With that, let me introduce our seminar speaker today. So our seminar speaker is Feng. She did her undergraduate in atmospheric sciences at Nanjing University in China, and then got her master's in meteorology at the Institute of Atmospheric Physics at the Chinese Academy of Sciences. And then after that, she moved to the States, to the University of Michigan, which is actually where I first met her, where she did her PhD in the Earth and Environmental Sciences department, working with Dr. Chris Polson, who was one of the first people that I worked with as an undergraduate researcher when I was at University of Michigan. So we have some connections there. So we know a lot of the same people from graduate school. After graduate school, she went on to do a postdoc at the National Center for Atmospheric Research, focused on paleoclimate, which is also where we overlapped for some time. And then in 2018, she started, January 2018, so 4 years ago. Is that right? Yeah. Started as an assistant professor at the University of Connecticut in the Department of Geoscience. And just one thing I noticed from her CV is that even though she was only there for a few years, she already has received a citation for teaching excellence as a faculty member. So that's exciting. But I'll switch it over to the topic of her presentation today, which will be on past hydroclimate sensitivity controlled by Earth system feedbacks. So remember to turn that on. Take it away.
Right. Good afternoon, everyone, and thanks, Kevin, for that nice introduction. Today, I would like to talk about our recent study on drivers of changes in hydrological cycle during one of the exciting past warm intervals. Before I start, however, I would like to acknowledge my co-authors, Tripti Bhattacharya. This is the lady you see to the right of the screen. She compiled most of the hydroclimate proxy records that I'm going to talk about today, and also devised the data model comparison method. I would also like to acknowledge the participants of Plycine Modeling the Comparison Project, so all those people in the center picture here, who made their simulations available and accessible and made the study possible, right? Okay, here we go. Before I start, I know most of you are researching on present day and future climate. So I would like to give a brief introduction of what can past climate tell us about the future climate. Hopefully this will contextualize a lot of paleoclimate work that my group and many other groups are doing. So the answer is actually quite simple, and lies in this famous quote by Winston Churchill, who also quoted the philosophers before him. It says, those that fail to learn from the history are doomed to repeat it. And this quote is actually amazingly applicable for understanding our ongoing climate change in the context of climate evolution. The chart to the left, Kevin told me that some of you have read this paper. So the chart to the left shows the geological reconstruction of global mean surface temperature for the past 100 million years in red and orange there. Correspondingly, the gray curve shows the global reconstruction of CO2 together with its uncertainty in the gray shading. So to the first order, you can see the co-varying CO2 and global temperatures through time. The most intriguing feature on this chart, however, is the co-occurrence of past warm climates such as mid-Cretaceous, which is about 90 million years ago, early Eocene, which is about 50 million years ago, and Pliocene, which is about 30 million years ago, with the elevated CO2 level. And those levels of CO2 are those ones that we're going to see moving into the future. The amount of warming generated in those past warm climates are comparable to what might happen in future following different shared socioeconomical pathways. So the idea is that we could study features of past warm climates to gain insights on what our world might become like looking to the future. We can do this comparison of future warming and past warm climate states more quantitatively. The chart to the right here demonstrates this is comparison done through calculating multidimensional distance using seasonal temperature and precipitation in RCP 8.5 scenarios across a range of models, as well as paleoclimate simulations of last interglacial, pre-industrial, historical, Holocene, Pliocene, Eocene, and obviously there's also a non-analog option. If the distance is too big, then there's no known analog. So I can see that starting from the middle of this century, we started to see that the land area across the world started to show analog features in seasonal temperature, precipitation to Pliocene climate. By 2100, lots of land areas start to really look like Pliocene, and by the end, by 2200, we can see our world start turning into an Eocene-like world. Right. The perk of studying past warm interval is that we cannot collect observations of the future. Obviously, it hasn't happened, can't time travel, but we can collect observations of the past, and those observations will provide insights on features of high CO2 climate, which can then be used to assess model behaviors in simulating those high CO2 climates and provide insights about climate feedbacks, general large-scale climate features during warm climates, which might be something we are going to experience looking to the future. Traditionally, paleoclimate reconstructions are notoriously difficult to interpret and difficult to use because studies are generally published on one site or maybe a few sites in a limited area. And the information ranges from sedimentary record to geochemical record to fossil record, so it's really hard to use. Luckily, for the past decades or so, geologists have really come together and sorted out and compiled geological reconstructions and interpreted them on a mutual agreed basis. And those two maps just demonstrated the site availability for one of the warm intervals for this type of work. The top here shows the black dots on the top map shows the available sea surface temperature reconstructions for the Pliocene, and the bottom ones, all those sites, shows available hydroclimate reconstructions for the same Pliocene interval. So the associated data sets are usually, and this is done for other warm intervals such as Eocene, and there's ongoing work to do that for the Miocene as well. And obviously, there are results, or existing results for Holocene, for last glacial maximum intervals like that. So this associated data sets are generally published in the data compilation papers. I took a screenshot of 2 of those. And it has included like 30 or 50 authors, and the data sets are included as part of supplement. Now you can directly go download those data sets, and it will have the locations of the sites, the actual climate information that are interpreted based on the community agreement. So this massive community effort made evaluating climate models with paleoclimate data possible. And this work is coordinated again through Paleoclimate Modeling Comprehensive Project across the community. The goal is for participating models to conduct experiments with the same forcing and boundary conditions. The idea is very similar to CO2. So if we look at response differences across models, what we're really seeing is the responses generated by different model physics and dynamics. And we can then assess how well the models can hindcast past climate states with those large data sets generated from the geology community. PIMI4 on this chart here intercepts with SoMAS for a range of experiments highlighted in this green circle and green shading here, including a pre-industrial experiment, brought 4 times CO2 experiment with Holocene, last glacial maximum, the past millennium, past 1,000 years, last interglacial, as well as the mid-Pliocene simulation. So all those intervals have fairly similar paleogeography and topography to present day. As a result, the model behaviors in simulating those climates are likely comparable to the behaviors of simulating future climate. For this particular talk, I'm going to focus on mid-Pliocene warm interval. This is interval with 13 participating unique models that have run with the same set of boundary and forcing conditions and trying to reproduce climate conditions during this interval. To start, so why would we be interested in the mid-Pliocene warm interval? This interval between 3 and 3.3 million of years ago. You might think, wow, that's a long time ago. But really, if we look at the Earth's history, this is super, super recent, right? And this is the last time the CO2 has reached present day level. To the right, all those blue dots and curves shows the most recent compilation of CO2 reconstructions for the entire Cenozoic. This is some 66 million of years ago. The red dash here shows the 400 ppm CO2 level. Today, we're having 419 ppm CO2 level. And really, you have to go back all the way to the mid-Pliocene to see a similar level of CO2 to what we have today. We can take a closer look at CO2 reconstruction for this interval, which is highlighted in this red curve here. So this is to say we're zooming in to really look at this interval. There are some glacial, interglacial variabilities of CO2, but again, the mean state is still around 400 ppm CO2. It's around what we have for today. To the right, I'm showing a reconstruction of global topography and geography. There are small changes in the ocean gateway configuration for this interval around the Indonesian sea shelf. So the Sunda and Sapu shelf is perhaps shoring a bit during this time. Around the Arctic, there are perhaps also closed ocean gateways in the Bering Strait and Canadian Arctic Archipelago Strait. But the rest of the world basically looks the same as present day. Okay. Geological reconstructions of sea surface temperature generally suggest global average warming ranging between 2 to 3 degrees, accounting for the proxy uncertainty. So it seems peculiar when you think about this amount of global SST warming, because the global mean temperature warming from the pre-industrial from 1880 corresponding to the CO2 rise from pre-industrial level to what we have for today is only about 1 degree Celsius, right? Yet, just by looking at the global mean sea surface temperature, Pliocene climate relative to pre-industrial is about 2 to 3 degrees warmer. So we are, when we look at Pliocene reconstructions, we are looking at a much warmer climate compared to what we have for today relative to pre-industrial. Right? When we think about past climate, it's useful to pay attention to time scales of feedbacks in response to CO2 increase. All right. So what we're seeing, what we're experiencing today is really the short-term climate feedback, which to CO2 increase, which really involves changes in clouds, water vapor, snow, and sea ice at the time scale of years to decades, right? Typically, we estimate the amount of warming corresponding to this shorter term feedback with mixed layer ocean model to a doubling of CO2. And this estimate is called Charney sensitivity or equilibrium climate sensitivity. However, when we're really thinking about paleoclimate, what we're really looking at is an equilibrium climate, which also features responses of biome range, responses of three-dimensional ocean circulation, as well as responses from the ice sheet, right? So those changes contribute to either amplify or mute our short-term response over the time scale of hundreds to thousands of years. So how much does the long-term response contribute to surface warming of the Pliocene? I'm particularly looking at the Pliocene as an example. We can apply a simple linear forcing feedback framework to try to quantify the effect of this long-term response on the global temperature change, right? So the response-related response can be linearized, written as a feedback parameter times the amount of temperature change corresponding to certain CO2 change, level change. This can be decomposed as the sum of short-term response, short-term feedback parameter times the short-term temperature change plus the long-term response, the long-term feedback parameter times the long-term temperature change, right? And the total amount of temperature change in our fully equilibrated climate is the sum of short-term temperature change plus the long-term temperature change, and the feedback, the net feedback strength is the sum of short-term and long-term feedback. Following this linear framework, we can derive a regression between the additional warming by the long-term response as a function of short-term warming, and the short-term warming, like I showed before, can be estimated with the equilibrium climate sensitivity of individual models. So how does this regression look like for our Pliocene simulations? To the right, this shows each of those blue dots shows a model simulated Pliocene warming, either estimated by equilibrium climate sensitivity of that model, or this additional warming due to the long-term response by taking the total amount of warming minus the short-term warming estimated from equilibrium climate sensitivity. To note, the short-term feedback parameter is negative, which means the radiated response really compensates the forcing. As you can see, to start, almost all the models simulated the additional warming by incorporate the ice sheet, vegetation, and three-dimensional circulation changes, which means the long-term feedback is net positive. So the long-term feedback from those changes amplifying the warming, right? And the other interesting thing to notice is this regression here is moderately nonlinear and exponential, which suggests that in the suite of models participated in the Pliocene model comparison project, the model with a high climate sensitivity also turned to be more sensitive to this long-term response. Right. So today I'm going to focus on this particular study in which we explored the effect of this long-term response on hydrological cycle during the mid-Pliocene. The most pronounced feature of hydrological cycle changes associated with this long-term response is in the northern subtropics, which I'll show you in a minute. Our work is recently published in this Nature Communications paper together with the simulation data as well as the proxy compilation data. So if you're interested in any of this work, feel free to check out. But to start, I'll just show you some really first order large scale evidence for changing hydrological cycle in the northern subtropics during this time. To the top here, I'm showing a modern distribution of soil types. So I'm highlighting this area from North Africa, stretch across Arabian Peninsula, Mid East, and all the way to northern China. So soils around this region is currently dominated by antisols. This is unconsolidated sedimented rocks. And aerisols, this is soil forming in arid or semi-arid environments. Those type of soil profiles characterized by carbonate formation, gypsum formation, both are formed under evaporative conditions. If you look at the aridisol distribution for the Pliocene, which is shown in the bottom map here, is very much restricted to the northern side of the North Africa, Arabian Peninsula, with a little bit stretched towards the Mid East, while the majority of Central Asia and northern China now is replaced with something called mollisol. Mollisol is a type of grassland soil. Right? Vegetation distribution tells a very similar story. Present day in North Africa, stretching all the way towards the northern China, the landscape is dominated by desert, by dry shrubland, by dry temperate and dry tropical shrubland. A typical vegetation for this type of shrubland would be succulents. You have in your windowsill or cactus, right? So they're extremely drought tolerant. If we look at what the biome distribution look like for the mid-Pliocene, again, the desert is retreating northward, and this dry dry shrubland also retreated westward and limited to the Arabian Peninsula and areas in the Mid-East. Okay. However, this massive weathening of the northern subtropics, as shown by the soil and vegetation large-scale reconstruction, it cannot be, or is very different from what we know about future hydroclimate changes following an intermediate middle-of-the-road emission scenario, which is thought to be comparable to the mid-Pliocene climate conditions. The top chart here shows the estimated monsoon range following the RCP 4.5 in CMIP 5 assessments. So compare the black and the red highlights the future potential changes in the monsoon area. And the change is actually quite subtle. If we look at the East Asia, there is around 10% expansion northwestward of the monsoon. However, the dry area in the Midwest and in the North Africa, which is highlighted in the gray contour here, stayed really constant. And even this monsoon expansion is a pretty subtle signal. I also checked on the terrestrial water balance calculated by precipitation minus evaporation and compare the predictions for the end of 21st century to the end of 20th century following the SSP 4.5. And you can see to the first order, the P minus E changes, especially across the ocean, looks very similar to this wet gets wetter, dry gets drier paradigm, right? You see a giant weathening across the equator, and you see drier or reduction in the P minus E of the equator. Across our interested area, North Africa, all the way to northern China, however, the change again is very subtle. However, in our simulations, we did simulate, in our Pliocene simulations, we did simulate this massive positive P minus E trend stretching across the northern subtropics. So first thing to note is when we overlay the proxy hydroclimate indicators, so those are the soil record, those are the vegetation record, and those are the lake records. So actually, when we overlay those terrestrial hydroclimate record to the first glance, it does seem to match with our multi-model made. But in the study, we wanted to go one step further. So can we actually use those proxy records to evaluate the model skills? Like I mentioned before, we have 13 simulations here, and we're showing the multi-model ensemble. But can we actually quantify how well each of those models actually did by comparing to the categorical proxy data? The way we end up doing this is by calculating a categorical correlation called GRATS AC. So in order to do that, we have to convert our model simulations also to categorical data. In order to do that, we have to define a threshold for dry, neutral, and wet in our model simulations. So if the simulated P minus E changes in our pricing simulations is below the negative of that threshold, we see the model simulation at that location is dry. If it's between a minus and plus of that threshold, we say that the model simulation at that location is neutral. If it's above the positive threshold, we say that the model simulation is wet. Right, so in such a way, we can convert the model simulations also into categorical data, and now we can calculate our categorical correlation. Right? Here's some results. This chart here shows the model, the categorical correlation GRATS AC for each individual models corresponding to a range of P minus E threshold to define the categories in the model, right? So you can see that even just by looking at this broad scale hydroclimate proxy data, we can start to evaluating model skills, start to find certain models that are pretty good at reproducing this wettening trend, while some models that are not very skillful, for example, NOR, ESM, and GIS model are generally not matching the proxy data, while the EC-Earth-3 has really high skill at reproducing the pattern, the wettening pattern we see in the proxy data. Right. One step further, we also looked at, so what are the other variables in our simulations that seems to separate the model skill. And the key variable we find is actually simulated the total amount of warming in each of those models, right? So this chart to the top shows the GRATS AC estimated for a threshold of 20 to 60% as a function of simulated amount of warming by individual models. And you can see a pretty good linear relationship. The models which are producing more warming, incorporating both CO2, vegetation ice sheet changes in the model, also turn to produce a wetter band in the northern subtropics and matches the proxy better. However, the other interesting thing we find is the correlation between model skill and equilibrium climate sensitivity, which essentially captures the shorter term response of the model, is actually much weaker. So, can we quantify contributions separately from prescribed changes in CO2 and other boundary conditions in our pricing simulations? We can do that with just one model, right? I can't run none of those models, but I can run one model. This model we're using is Community Earth System Model version 2, which is probably not a new model for most of you. This is the same model used in the IPCC AR6 and SIMAP6 report. We run the model consistent with consistent resolution and consistent physics and dynamics as the future projections, except in order to cover the deglaciated Western Antarctic for pricing, we extended the ocean grid and ice grid by 10 rows in the Southern Ocean. All the simulations we're talking about here are equilibrium simulations. So it has run for hundreds to over 1,000 years for the top of atmosphere radiation imbalance to reach 0. So here are the set of simulations. To start, we're making use of existing pre-industrial simulations. I'm denoting this as E280. I run a separate simulation in which I increase the CO2 to the pricing level to 400 ppm, and this is the E400 simulation. So the comparison between E400 and E280 tells us the response due to CO2 increase without any other boundary condition changes. Right? I also carried out a simulation featuring the pricing, topography, and geography, but pre-industrial CO2, right? So the comparison between EO280 and E280 tells us the response solely due to the changes in geography and topography. Lastly, I carried out another simulation in which I featured pricing, topography, geography, but this time it's 400 ppm CO2, and this is EO400 simulation. So comparing this EO400 simulation with our full forcing simulation featuring CO2 ice sheet changes, geography, and topography tells us the effect of vegetation ice sheet changes, right? So the difference between EO400 and the EOI400 is due to the prescribed vegetation ice sheet. Let's take a look at what we get. The effect of CO2, no surprise. Again, across the tropical ocean features wet gets wetter, dry gets drier to the first order scenario. The changes across north and subtropics is generally pretty subtle and very localized. There's a little bit of contribution across the Tibet, but overall, this pattern we see in the full forcing experiment shown in the top red corner here is not reproduced by only inducing CO2 increase. Similarly, paleogeography and topography also induces some tropical P-E changes, especially around places where the Indonesian sea shelf has shored. But across the northern subtropics, the response is localized and failed to reproduce the full response. The only experiment we tested actually reproduced the full response is this pair of experiments featured the ice sheet and vegetation changes. So through those experiments, we can conclusively say that the subtropical, northern subtropical wettening signal in our pricing simulations is primarily attributable to vegetation and ice sheet changes. We're also curious, so through what kind of dynamic mechanism do our simulations generate this wettening of the northern subtropics? We analyzed the dynamics using the moisture budget analysis, which is following the equation from Seeger and Henderson paper. Precipitation minus evaporation is balanced by the tendency of moisture content in the atmosphere column and the convergence of column integrated moisture flux. Right. We did two things, which perhaps also being done by other researchers. We did two things to further decompose this moisture budget. One is to apply a small perturbation method. So a quantity, either humidity, velocity, P-E, or surface pressure in our sensitivity runs is the sum of the same quantity plus a small perturbation. The same quantity are control runs and plus a small perturbation. We also apply the Reynolds decomposition to decompose changes into climatological mean change and a deviation from that. So after we apply this, reorganize all those terms we have. Turns out we get 6 of those terms. Term A describes the changes in the seasonal cycle between a pair of experiments. So those 6 terms describes the changes in P-E climatological mean changes in P minus E between a pair of experiments, right? So term B now really showed up to quantify the thermodynamic effect, which is to say that if we assume that circulation doesn't change, what happens if we have changes in the tropospherical humidity? Term C here is to say that if the humidity doesn't change from the control, what might P minus E would change if we have some changes in the zoonoid mean circulation. And term D shows that this humidity as the same as control. What is the P minus E change associated with changes in the asymmetric component or the stationary wave component of the circulation? And we have term E and F, which separately describes the covariance between humidity and circulation, and the residual term incorporating changes in surface fluxes and eddy fluxes. Right? Actually, four of the more pronounced terms, changing seasonal cycle is very small, and the covariance between circulation and humidity is also very small, so I'm not showing here. But I want to highlight those four terms. To the top here, we have changes in P minus E associated with zoonoid mean circulation. And you can see for the region that we're interested in, the Sahel region, and I highlighted the East Asia region. This term doesn't really contribute a lot to the P minus E changes. The term that contributes the most are the stationary wave changes. You can also see the wind vector shows the changes in the asymmetric wind between Pliocene and the pre-industrial, as well as the thermodynamic term. This decomposition is done for the summertime in the northern hemisphere. So the climatological mean circulation for the summertime for the northern subtropics towards convergence towards the western African monsoon and the south and eastern monsoon. Under this circulation pattern with increasing moisture, you are going to end up having more moisture convergence even without changing the circulation pattern. So that's what is illustrated in the thermodynamic term. Locally, you do see some pretty noticeable influences from the residual term. However, when we average across this region, the contribution of this term is fairly small. I also want to highlight that those two terms are really sorting the model simulated P minus E for both the tropical East Asia and Sahel region. The thermodynamic term, you can see the simulated P minus E in individual models is strongly sorted by the thermodynamic term, as well as the stationary wave term in both regions. As it turns out, if we take the average for those two boxes that I showed before, this moisture budget in the ensemble mean, showing the blue bar here, is consistent with just a single model CESM2, showing the red bar here, which then is completely reproducible, the moisture budget, just with vegetation and ice sheet changes. So now we have all those steps for analyzing the dynamics, provided us the linkage between the vegetation ice sheet change simulation as well as the full simulation and the ensemble mean. So in general, we can say that the ensemble mean is also very likely driven by the vegetation ice sheet changes and mainly through changes in the thermodynamic term as well as the stationary wave. The question now becomes, so how on earth does vegetation ice sheet changes change the thermodynamic term and change the stationary wave? The thermodynamic term is probably the easier to link to the vegetation change. To the left here, I'm showing the prescribed biome types, essentially, In our simulations, I want to draw your attention to this green band across the Arctic region. That's where the expanded, that's where the expanded boreal forest during the mid-Pliocene is located. Also, I wanted to draw attention to this reddish patch stretching again from the northern China across Central Asia, Mid-East, and across the northern north of the Sahel. So this is where the grassland has replaced the dry shrubland and the desert that I just mentioned before. Correspondingly, you see this massive increase in surface latent heat flux, which is indicative to the massive increase in evapotranspiration through the biome changes. So essentially, in our simulations, this enhanced evapotranspiration added lots of moisture, lots of water vapor in the troposphere, which again amplifies whatever climatological moisture convergence you have for this region. So what about stationary wave response? Here I'm showing a map. Let's first take a look at what it looks like to start, right? So here I'm showing a map of 600 hectopascal January to September average wave number 1 of stream function differences due to the vegetation ice sheet changes, right? This is done through Fourier decomposition. We choose wave number 1 because it contains the majority of wave energy. The corresponding rotational wind is also plotted here in those blue vectors. You can see, following these blue vectors, you can see this massive moisture influx and recycling going from the tropical Atlantic, tropical Indian Ocean towards the North Africa and towards the Central Asia. And this circulation pattern generally matches the asymmetric circulation pattern that I showed you before. A potential linkage between vegetation changes, showing the left again, and the stationary wave changes is perhaps through the surface temperature pattern. And the surface temperature pattern can be explained by the surface albedo changes, showing in the right here. The blue area is where the surface albedo has lowered, again corresponding to the screening of the continent. Corresponding to where this albedo has lowered at regional scale, we also see enhanced regional warming, and corresponding to this enhanced surface warming. If you still remember how to draw the thermal wind relationship, you can draw the diagnostic thermal wind on top, which is in the blue vectors here. You can see that this wave centers is not, and the corresponding rotational wind is not that different from the diagnostic thermal wind relationship. So essentially, in our simulations, we think what we see is really the surface temperature pattern, the surface warming pattern, is generating the stationary wave response. And the surface warming pattern is linked to the surface albedo changes due to the vegetation change. In conclusion, we find that the mid-Pliocene waning of northern subtropics is largely a result of vegetation ice sheet changes, and through two conduit. First, vegetation and ice sheet changes act to enhance the evaporation and to enhance the tropospherical water content. And second, it generates regional warming pattern and stationary wave response. The other interesting thing, to me, I find is small scale at simulating those weather subtropics strongly scale with small sensitivity to vegetation ice sheet changes, and proxy data seems to suggest seem to support the higher sensitivity end of the models. Right? Implications to future climate. So dynamic changes in vegetation, including vegetation range shift, may have profound influences on future hydrological cycle, and currently we're not simulating the dynamic range shift when we're looking at future climate. There are already indications on the leaf area changes from past satellite observations, a lot of area on land are getting leafier. But besides that, it's possible that the redshift may also happen when we're looking at into the next few decades or next few centuries, and those changes we're still yet to consider. And in our simulations, those changes perhaps could have profound influences on hydrological cycles. Right. Thank you so much for your attention. I think I almost, did I run out of time? Okay, I think I still have time for questions.
We'll open it up, maybe first questions in person, but then I'll check. If you could raise your hand on Zoom, I'll also call there. So yeah, Ming-Hua.
Yes, so for the ice sheet changing, do you change in the Greenland and the Antarctic both, or just the Greenland ice sheet?
I changed both actually.
10 grades for both sides?
Oh no, just to the Antarctic. So I'm sorry, let me go back to the geography. Yes. So in this map, you can see that this area, that's the Western Antarctic sea shelf, which is deglaciated based on geological reconstructions for this time interval. So we extended, well, the model grade, ocean and sea ice grade only extend to like right here, the present day continent. Because this area in the present day simulation is treated essentially as a continent. But in our simulations, it's ocean. So we extended the grade further south. In the Northern Hemisphere, we don't have this issue. So we didn't have to extend the grade.
Okay. And so do you know the relative significance of the ice sheet versus vegetation in explaining your, say, simulation results?
That's a good question. My suspicion is perhaps it's vegetation, just because we see the
albedo.
Yeah, we see the albedo response and the latent heat response really matched up with the vegetation change. But I haven't done the ice sheet sensitivity by itself yet. Yeah, I still have to do
So
that.
then the vegetation change needs to respond to something, most
Yes.
likely precipitation, right?
Yes, so
And so then the cause and the effect
yeah.
is not that clear. It's like why vegetation?
Yes, so yeah, you're right. So we don't have that's why the dynamic vegetation model would be really helpful for this case in those simulations. In those simulations, we're treating the vegetation change as boundary conditions, essentially the biome range as boundary conditions, and those are based on reconstructions. So this map. So if this is to say that if we know this is biome range as a part of the response from vegetation, so what kind of hydroclimate state is that going to be generated in equilibrium with the state of vegetation? And this is the result we get, which almost suggests that this grassland perhaps could be supported through a coupled dynamic vegetation simulation. Yeah, but we don't have that in the model.
So the two are consistent.
Yes, so to an extent, yeah.
So maybe I'll just follow up on that question. Is there a way you could set up like some mechanism denial experiments where you could like change the vegetation but keep the albedo the same, or vice versa, to kind of see, to kind of look at albedo versus maybe evaporation?
Yeah, evapotranspiration changes. Yes, so there is a simpler version of the land model which allow you to prescribe changes in like biophysics in the model. That's a good question. I haven't done that. But yeah, that's a good suggestion. We could prescribe, instead of actually looking at the vegetation, we could just prescribe what are the by the physical effect of vegetation, albedo changes or evapotranspiration to really look at the mechanism. Yeah.
You could lose years of your time trying to deal with the land surface file it puts.
Yeah, actually, I was very interested in fixing the land surface temperature. If
Yeah.
any of you guys know how to do that.
I don't. Any other questions, maybe in person? Go ahead, Christopher, and then we're going to go on Zoom, and then we'll come back in person.
This is more of a context question rather than about the actual talk. But in the in your plots showing the CO2 in the mid-Pleistocene warm interval, it appears, and it could just be a scale thing, but it looks like the CO2 suddenly went up by a lot and then back down. And is it known why it did that?
I think from the 3.1 million year to the 1.25 million year, there's a hiatus in the record. So there's
yeah, but it's still like a lot higher. And then you had a longer one where it just went.
Yes.
Yeah, there. So
Yes.
it's like it's quite a bit higher than it was in the several million years before and after.
Yeah. So CO2 declined from the mid-Pleistocene, actually from the end of the Pleistocene all the way to the early Pleistocene, and then it was oscillating around the pre-industrial level for a long time. So that's a general.
Yeah, but I think he's asking, so like this
Like
specific
why does
peak,
there a big spike?
do we know why there's a big spike?
Oh, why there is a particular peak?
Yeah. Which is this warm period.
That's a good question. I think partly on this map is because there are a whole bunch of data on the Pleistocene which got squished.
Okay.
There,
It's just an artifact of plot.
yeah, it's perhaps just the artifact. When we look at, I don't have a long-term record here. Yeah, so if we look at, I'll just draw it hypothetically. If I were to draw a actually stretched CO2 record for the Pleistocene, it would be a little higher for the early Pleistocene and go down a little lower to the mid-Pleistocene, and then have a decline at the end of Pleistocene corresponding to the Pleistocene transition of the northern hemisphere ice sheet expansion. And then going to the Pleistocene, you start to see this typical like oscillation between glacial and glacial cycle. Yeah, I think this record, this peak is an artifact that just happened to have so much more data for the Pleistocene compared to the late Miocene.
Okay, so maybe we'll move to our to Zoom real quick. So I think Edmund, you had your hand up first, and then we'll go to Malcolm.
Yeah, hi, this is Edmund Chan. Nice talk. I have a question. Actually, my first question was similar to what Minghua asked, so you already answered that. But following up on that, is that it seems that the response to the vegetation seems to be very important. The question I have is, because I don't know that much about land model in the GCM. So how well are they verified? And you separate those into different types of land surface, and then each land surface has a response to the change in wetness, change in, and dry, driven by the atmospheric and components. So how well are those land surface models validated, and how much can we really trust the response to really the change in the vegetation?
That's a good question. Actually, so a lot of those models have separate. So a lot of those models are also used in SoMAS 6. So they're validating like the land model performance is a separate topic. So I trust that most of them are state of the art. So actually, I don't really know the modern skills of those models in simulating present day land surface conditions. For the Pleistocene, however, based on our results, I'm showing this GRADS AC, which is like a skill assessment based on the proxy data as a function of surface temperature. And this seems to suggest that the models, perhaps with a more sensitive, actually this plot might be better. So the models that are perhaps more sensitive to land surface condition changes are also more likely to reproduce this wet condition as suggested by the proxy record. So I can only tell at the moment that from the pricing, from the proxy perspective, I think ECR3 seems to perform the best among the suite of the models in simulate this wet condition. But I have to check whether ECR3 also reproduce present day land surface simulation well as well. Yeah.
So I think Malcolm, you had a question?
Yeah, thanks, Kevin. Well, thank you. A very interesting talk. Also very scary, looking at 2100. But I just have a question about other greenhouse gases of the, say, the mid-Pliocene, such as methane, and maybe you know more about water vapor from the hydroclimate. Could you just mention that a little bit?
Yes. So for past climate, because the oxidation rate of the oxidation timescale of the methane is only like a couple thousand years. So the idea is that if you estimate after a couple thousand years, it becomes the CO2, right? So the idea is that if you estimate the CO2 level, it should already incorporate, let's say, the methane emission, unless there is a continuous methane emission to the atmosphere through time. We don't know a lot about methane emission at this time from the geological records, but you are right. There is a PNAS paper that actually has a interactive methane component in one of the versions of the, I think it was one of the UK land models, and they did find that through this wettening, through this creation of wetland, there could be an additional warming component from this continuous methane emission. But we don't have that in our model.
Thank you.
Yeah.
So maybe we have time for maybe one more question from the person. So yes.
Yeah. Maybe a little off the wall. The community that's looking at anthropogenic climate change over the past 100 years or so is looking a lot at gross primary production, GPP, global, and plotting it, for example, against CO2 and getting a fertilization coefficient out of that. I'm wondering if your community at all looks at GPP and its dependence on CO2 and other variables.
I haven't, well, as far as I know, for the pricing, we haven't really done that. In our simulations, the simulated, in the CSM simulations, we can simulate the, so we prescribe the type of vegetation, but we allow the phenology to vary. And we allow the terrestrial carbon cycle essentially to vary in those simulations. And we did simulate a increase net primary productivity actually corresponding to this wetting band. So I think that's kind of, what's the word? That is consistent with a lot of people, what a lot of people are thinking about changes in like the productivity in response to increased CO2, you're expecting an increase in the net primary productivity from the forests, from the grasslands. In our simulations, the other interesting thing we find is so a lot of those. Let's just say like when we look about anthropogenic climate change, a lot of that is due to the CO2 fertilization effect. But in our simulations, even without CO2 fertilization effect, by generating a wetter climate in general over this region, we can also generate more productive grassland forests in this region as well.
I'm not necessarily endorsing that concept of CO2 fertilization, but I think GPP is an interesting variable in and of itself.
Mhm. Yeah, yeah, I haven't done much research on the GPP as a function of CO2. This is actually dynamically simulated in the simulations. So I'm currently taking it as what is coded.
I would think it's a variable that you might be able to get out of your calculations, maybe useful to look at.
Yeah, yeah, I haven't thought about that yet, but that's a good idea.
Thank you.
Okay, so well, let's think. Run one more time.